who have already worked on ANN. So there is a small difference, although I think that most of you might be already understanding this part. But if anyone is a beginner in this, why we prefer CNN over ANN, or what may be the major benefit or drawback of one to other, so that we need to discuss first. So in case of ANN, basically ANNs are very basic models. If you have gone through the structures of ANN, they just have like a limited set of hidden layers with a limited capability of handling data sets, like very huge data sets we cannot process inside your ANN. So generally, when there is a large sized image, it is better to have a CNN model because that has more computational complexity with better ability to handle multiple channels of your images. One more part, with your ANNs, they are more sensitive to location of the object in the image. That is one more part, because they are very basic models. So if at specific location there is a specific object or specific pixel pattern they are understanding, they will stick to that. If we find certain variation in that, they will fail. For example, if we have like a simple example of dog cat classification, it is not possible that all the images of dogs and cats will be in the same posture. We'll have any different posture of those dogs and cats, and the features will vary depending upon the different pictures or different pets. So in such cases, your ANN will be giving very small accuracy due to the reason that the change in feature maps, it cannot observe very clearly. So that is why your CNN are more useful in that case, because it works with automatic feature extraction. We are not limited on the on just on the manual efforts to extract features like we have in case of machine learning or basic models. In CNN, everything happens on the layers that we have discussed yesterday also. So even if not all the layers are fully connected, there are some partially connected layers also in between, but still it is capable enough to drag more of the patterns from the even from the larger images and videos, and that can bring us more relevant results. And it is definitely invariant to the location of the object, so that even if there is some distortion in the scene or there is a certain change in the frames of the video, everything it can track more precisely. That brings some benefit to us in comparison to your other model. So while moving ahead with this, there are few layers that we have already discussed. These basic layers of CNN we have already discussed. Moving further, there are few additional layers that we add into the network to enhance its capabilities. That includes your batch normalization layer, we have flatten layer, there is a dense layer, and we also have dropout layer. So they make some additional elements into the system design, and they will help you to improve accuracy of your model very precisely. But we need to understand how we use them and how they cooperate with your existing basic layers in the network. So both things we are trying to understand here one by one. I hope we all remember these basic layers. Input layer, we have already understood that it will just process your image pixel patterns. So yesterday I talked in terms of grayscale image. We had one single pixel element from there, and that we were having a one-dimensional array. From there we were managing everything. But when we talk about a color element, that is your RGB pattern, we generally have 3 different channels extracted from your image. So the pixel values of red, green, and blue that generate the specific color that we need at that specific pixel point. That you definitely must be easy to understand that, because how RGB combinations works generally in the color map also. The same thing is working here. So that
Madam,
is
one
how
question.
colors
Madam,
into, yes, please.
Madam, one question is that how you decide the input layer size. Suppose I have a extra image, sometimes you also on big images. So in order to input this image value into the input layer, we have to find out number of neurons to put in the image values. Now, how you decide the size of the input layer? Suppose the standard input layer is using 64 neurons. In case the image size is big, you have to put input on the scale. So obviously input layer size will be increased. Now, there is any standard method for deciding the input layer size, or by default you have to use any input layer size?
Sir, the practical way that we follow is the recommended option from the experts is we always prefer small size in the beginning, because if we add more neurons in the beginning, it gets difficult to extract relevant features. So although this involves a hit and trial, but the recommended part is you start from 16, you try 32, you try 64, and see which one is more suitable based on your real time images.
But in case of standard input data like data features like that, in cases suppose we have 17 or 18 features on there, easily we can input in the input layer. But is the number of more features is included for deciding the best class of prediction? So in that case, obviously input layer size will be increased. So how we there is any standard method or anybody can use any type of.
Sir, excuse me, sir. This FTP is not designed for your questioning answering right here. So first you listen the complete lecture, then you can ask the question. There are 67 participants right here, and right now you first listen all the topics. We have to cover the complete session for this CNN.
Okay, sir.
So first listen, then you ask the question. In between, you are stopping, and then you are asking question. It is not a right way.
Okay, sir. Okay. Thank you, sir.
So we are talking about RGB images over here. We have three different channels in case of RGB, and the mixture of pixel elements out there decides color for the picture. So in the same pattern, we are going to process it. So what we do when we are processing it, yesterday also we have seen that in the implementation, that we generally need to normalize your pixel patterns out there. So the idea is to bring this 0 to 255 range to 0 to 1. The concept of this we have discussed in past 2 days. Repeatedly we have discussed that we have to normalize so that our model can have better prediction ability. So that normalization process we can do by using different methods. Yesterday we have done one part is that was with your image size, we have divided by 255 and then we subtracted with 0.5. Sometimes we just divide by 255 and we do not add any subtracting factor. That completely depends on what type of normalization we follow. So there are several procedures that are defined in your literature also, where you can find it easily and then you can deploy it from there. Further, what we have is while processing these different elements, every time you will have different width and height of your these pixels. This simple example we have just with the 4 units only. So 4 pixels width or height wise we are just displaying here, but this is not the actual case. When we are presenting real time images, maybe gathered from CCTV cameras or from satellite cameras, they generally have a very huge size of this filter. This input layer. So that will include like 1000 cross 1000 matrix or sometimes 500 cross 500 matrix, and there will be so many RGB elements based on that scattered around with 3 different channels. So accordingly, all the further processes we may have to do. So while working on this concept also we discussed yesterday, that there will be some convolution layers added into the network and we'll decide some filter sizes based on this. So this thing we already discussed. I'll not go in deeper with this, but we know that we have to decide the filter size. We have to choose the stride for this, such as first we'll start from here. If 3 cross 3 filter is there, this will help us to put up this element. Then we will have a stride of 1, for instance. We'll have second element from here, and we'll keep on filling these values in sequence. So once the first layer we have extracted, this process we have discussed yesterday, so I'm not updating it again right here. So this filter will just keep on moving like this, and entire feature map we are trying to extract from this. So now one important parameter or one important term we are getting here is feature map. What it is and how it is being generated, what we are getting in the output. Although we just understand that we are just doing convolution, and that as an outcome it is providing us a feature map. But if we want to go little in depth with this, let us have a quicker look on the whiteboard. I'll discuss few factors about feature map that as a beginner you may need to know. The first thing is the feature map is basically the output of your convolution layer when we apply specific kernel or filter over it. So whenever we pass those filters, they are going to produce multiple feature maps. Multiple feature maps by following your different weights inside your kernels that we discussed yesterday also, that they start with the random values, random weight values inside kernels, and then we try to extract iteration after iteration the accurate values it will try to extract. So whenever these filter elements are applied, they will always try to extract some specific elements from the high level pixel values. They will create low level features. And for instance, we have one image like this that we studied yesterday also. So it will have several pixel elements. So then I add one filter from here, like maybe of a smaller size, and we apply it on this, and ultimately as an outcome will get your feature map. So this feature map again is going to have several outputs. But what it is basically going to extract when we convolve, so that may include information about texture of your image. Sometime one feature, some kernels will get information about edges of your image, lines of your image, corners of your image. So how that weight updation we have added into the kernels, and how those kernels are behaving with your convolution process, accordingly the extraction will happen. And these parameters, basically we have an ability to update them while building CNN model. Currently we have worked on the basic model only. There are many advanced things that you can do within the model itself. You can update its internal parameters also. We can do hyperparameter tuning that will help you to get specific elements out of it. Like if you have to give more focus to the edges, then we have a specific technique. If you have to give more option to the corners or lines or some specific pattern in the image, accordingly the feature maps can be updated with the kernel function. So for instance, we are considering one filter sequence with 3x3, and we have to apply it on a matrix, the input matrix of 5x5. It is likely to produce a feature map of 3x3 again. So in order to compute these elements, how it will work, that computation we have seen on the system also. It will go through the first element, then stride through the second, then stride through the third. So first element, second element, third element. So go downward, start from here, then this one, and then this one. So fourth element, fifth element, sixth element, and similarly on this section also. So depending upon how big is your this input image, accordingly 9 elements we are extracting from here. But in these 9 elements, what values we are going to extract, that is also an important element. So depending upon how the filters are organized, the feature maps will be updated. Like for instance, when we are planning to extract specific like horizontal edges from your input feature, so maybe a filter like this will apply, maybe like -1, -2, -1. Middle ones will keep 0, and last one like maybe just some random values I'm updating. Means when we are targeting the horizontal edges, there will be certain high range values on the horizontal edges. The middle ones we are keeping zeros, because we don't want to put more focus on the middle values, rather on the horizontal edges. So as this filter move on your images, it will put more focus on the edges of that area. Similarly, in case if you have another filter that you will apply on the system, and in that possibly you are planning to extract maybe horizontal edge, or maybe sometime vertical edge. Horizontal edge we have covered. In case if you are focused on vertical edge, so again we can organize something like this. So in that case, you will add some elemental values on the vertical side. So now it will focus more on the vertical edges of your image, and this is how it will just stride through entire feature, and it will get the feature map based on these aspects. Further, the size of this will also vary, because it is not always necessary that you will have a specific filter size. Only 3x3 filter is valid. That is not always possible. Depending upon how big is your image, and how many features you want to extract, what stride size you want to use, all those things matter into the CNN design. For instance, we say that we have an input image with size 28x28x3. 3 here means RGB channel, that yesterday we were using 1 with the grayscale. But if we have RGB image, definitely it will be 3, and this will be your matrix size. So then possibly if you're trying to use a filter size of 5 cross 5 cross 3 with the 3 channels again, so in that case maybe you will update a stride of 1. Again, the feature map that will be produced will depend on the stride also. Like if that window shift is by 1 pixel, the filter size in the output will be also different. The feature map will vary accordingly. If the stride size is 2, again the feature map will reduce, the size will reduce accordingly. So how we switch between 1 pixel to other, that is also going to change your feature map. So in this particular case, what we will have is the output feature map is likely to have a feature outcome, like maybe for example 24 into 24 multiplied by k. So in this case, this k value will depend on how the dimensions we are updating. Like if we are applying 2 filters, so ultimately 2 filters will be updating here, so that size based on 2 filters will become 24 cross 24 into 2. That will be the output in the ultimate scene. Otherwise, maybe if you are applying sometime in your these CNN layers, we go ahead with like 16 filters, 32 filters, or 64 filters. Yesterday also, I think we started with 32 filters when we designed our basic CNN model. So when we define your model like convolve 2D, and we add first element like 16, then we add filter size 3 cross 3. So what it means, 3 cross 3 is your filter size, and this one is the number of filter you are applying. So based on this, ultimate feature map will be generated. This k will be updated accordingly. So this is now going to determine how in-depth operation your convolution layer is going to do there. And this filter calculation that we are updating here, all these things, this you cannot always specify it with for every different data set. We always go with initial positioning, like a random setup we use initially, then we see how our model is performing. This is same as ANN also. If any of you have trained ANN models, there also this thing happen. We start with some random values out there, we apply weights randomly, we apply some functions. For the activation function also we apply randomly, then we see how our model is performing, then we change one hyperparameter, we see output how it is changing positively or negatively, then we create balance between multiple hyperparameters, and then finally we get some output. So this is definitely a lengthy process. When you have to design a model that is field deployable, it requires so many things in between. You cannot always be sure that yes, today I got a data set, I'm just putting 5 layers of convolution 2D, and just within 1 hour I'll be getting 100% accuracy. That is never possible. This is all adjustment between hyperparameters of different layers. And again, there will be one more part that we are going to learn, especially today. Yesterday, we created a simple convolution 2D system. One layer of convolution 2D we added, and one pooling layer we added, one fully connected layer we added, and the model was done. But when we talk about actual deep learning model, there will be like hundreds or thousands of layers sometime. So we just keep on adding layer after layer after layer. Like this convolution 2D itself, we declare like 5-6 times. For example, a minimum model we are creating, like I'll declare this 5-6 times. I'll put up few more layers in between, then I'll initialize convolution 2D again. I'll put up more layers in between, I'll initialize convolution 2D again. The idea is to extract more and more feature maps. On every layer addition, I'll try to update my feature maps with better clarity. That is the main idea of having these deeper networks. So when we'll design today's model also, there also we will add multiple layers. We generally start in the first layer, we generally start with lesser number of filter. So for a very small data set, you can even start with 8 filters only and see how your model is performing. Then you switch to the higher level of filter, like maybe 16 you use, or you go with 32. And even sometimes we change the kernel size. However, this kernel size usually depend on how big data set also you have and how much time, complexity, etc. you want to compromise with your model. So all those things we are going to apply based on the data set as well as the other parameters that we need from the model. But yes, these parameters definitely you can change based on the requirement. Even after this also, we have several parameters that are updated into CNN model, but as a beginner we rarely think about them. We generally start with the basic parameters only. Later on, when you go ahead with the advanced things, you will learn many other things about this, like internal parameters, like hyperparameters you can tune, you can have activation function tuning, all those things one by one you can update in the system. So the main idea behind doing all these calculations, updating all these parameters one by one, is that you have to design something that goes with the specific edges, corners, shapes, or texture of your input image. We need to learn every pattern from your image. And that we do through your convolution layer, your pooling layers. The main idea is to start from the higher level features and develop based on that. We design the more specific features, layer after layer, layer after layer, more specific features we keep on designing, and ultimately we are going to present the final pattern. And there is one important part to mention: CNNs are supervised networks, so the training always go with reference to label. That is the most important part. So that is how we are understanding, or how the model is understanding which features it has to extract. Because the idea is, like, for instance, if I have these 3 4 images, all of them are associated to a specific target. For instance, this is if I talk about yesterday's dataset, that was about digit classification. So maybe first feature figure image that I have is represents 1, second feature represents 2, this feature again represents 1, and this represents 3. So when my CNN will get this, it will first associate it with the label. Okay, this is 1, and model will understand, okay, these 2 are 1, and this one is 2, and this one is 3. Then based on that, it will just make a calculation that how many features or how many images I'm linking to this particular one. Because again, there will be like thousands of images that are linked to one only. Then it will track all the features related to one, applied with several filters, everything. It will try to create a match between them. That is the training process. Like, for instance, what we human beings do when we look at something, maybe as a child, when you teach your kid, you also present something to your kid time and again when there is a training phase of your child. Like, even if we talk about alphabet training of a child, we ask him to write A, B, C every day. Repeatedly he has to write. What is the reason behind that? He's drawing that pattern is in his brain. So repeatedly he's writing A, B, and C, and that pattern is getting printed in his brain, that okay, this is the way to write A, this is the way to read A. So that basically same thing we are doing with the CNN model. We are presenting this model time and again a image of one, so that it can understand whatever features are present in an image that contains 1. Similarly for 2, and all the digits that we have. And all this thing goes with the mathematics that we are applying on the layers, with the help of your convolution patterns, with the help of your different kernel sizes over there. So the same thing will work with your audio patterns, with the linguistic patterns, with the pattern of speech, or any kind of image that you provide. Everywhere the same thing will happen. We just extract some feature maps initially, and then we just keep on scrolling through all the essential elements by using kernels, and finally we'll get your outcome based on the most relevant feature maps out there. So this is a generalized process you have while training your model. Coming back to the PPT again. So activation function, one we have discussed yesterday, that was ReLU function, because that was the most essential function we generally have inside your CNN model. Other functions also are present there. We can have tanh, we can have sigmoid and linear. These 3 functions are more commonly used in basic ANN also. However, this ReLU is more relevant to your deep learning models. So the idea behind these functions, activation functions, is to add non-linearity into network. Because initially we can have any pattern of your input images or videos, whatever we are presenting. So how we are going to make calculation, or how we are going to make a decision about whether something will belong to one class or other class, that is based on your these activation functions. You can consider it something like in human brain we have so many neurons, and if you just understand the biological structure, those neurons either excite or they inhibit. There are 2 options. inhibitory neurons or exhibitory neurons. Based on what signal we are getting from the outside world, the neurons do some action. Like for instance, you have a situation where you are trying to cross a road, and in the meanwhile your phone also starts ringing. So your brain has to make decision whether it is better to cross the road safely first, or the person has to take the call first. So maybe you will just look at your phone screen and you will see if there is an urgent call or not. So all that process is happening in the neurons. Basically, we do not realize that, but it is actually happening on the neurons. So based on whether your call is urgent or not, how that decision is going to be made, some parts of your neurons or some parts in your brain are going to do excitatory action, some are going to do inhibitory action, considering which task is on higher priority. The task which is on the higher priority, that will have a sequence of excitatory neurons. The task which has lower priority, it will get an inhibitory sequence of neurons, and accordingly the final signal will be generated by your brain, whether to cross the road or whether to pick the call. So the same happens on the CNN also. And this thing, in case of our brain, we have electrochemical signals for that. We have some synaptic gap in our brain that works between your neurons, and that synaptic gap or that electrochemical signal helps us to make decision in one way or other. In case of our CNN models, the same thing is done by these activation functions we have inside. So they will basically follow the entire calculation behind the weight updates, the feature maps, everything they will understand, and they do mathematical calculation over that. So like if we have a two-way decision, maybe like this ReLU function that we discussed yesterday. So if something falls in the negative side, it will consider that 0. If something falls on the positive side, it follows a linear approach for that. There is a leaky ReLU also. That leaky ReLU function is one advanced version we have. In that case, instead of considering everything to be 0 in the negative side, there is a leaky portion, like a very small leakage we consider, like maybe up to 0.01 or 0.1 sometime. Up to that level, it will give you some values in the negative side also, instead of considering everything 0. So that small portion on the negative side that we call it leaky ReLU, because on the negative side, it will consider some minute values. And that function is also relevant in some cases. However, we generally start basically with ReLU. But still, if you have to do some advanced modelings, we can experiment with different functions out there. So there will always be a mathematical calculation that will help you to make decision how we are going to approach to one. Like for instance, if we have two decisions to make, cat or dog, for that some mathematical outcome you will have. So if total is 1, maybe dog will get like maybe 0.95, your cat will get like 0.5. So this one is on the majority part, then your model will make decision that okay, this image belongs to dog, and the remaining this is the lower probability, so cat will not be considered. So these are the mathematical calculations that are happening behind. This happens on every layer. Like whenever we are getting a bigger feature map, depending upon how many kernels we have applied, everything will pass through a activation function that you have applied to add your sequence of elements based on the decision making we want to have from there. Now we come to another important additional layer that we add, that is your batch normalization layer. This we have not discussed yesterday because these are some additional layers we update into the network to make it more stable. So what these extra layers do basically, they perform standardization or normalization operations on the data coming from the previous layer. We discussed that every time when we are applying a feature map, a new calculation is made on your model. That we have seen already, that when we use that stride, every time a filter is moving on your feature map, and it is giving you some outcome from there. So those calculations will result some numbers. We add a batch normalization layer in between, and it does normalization or standardization, but not for single pixel value. The one that we used initially, that is with your image information divided by 255, that is for every pixel element we are doing. But this one does it in the form of batches. It will consider multiple batches of your pixels and it will apply normalization on that. And those batches are basically decided based on different hyperparameters that we tune inside CNN layer. So there may be so many layers, like thousands of layers we can have within the network, and every time some updates will be making through this. So layer after layer, some calculation is being done. Like for instance, if we are using standardization, then maybe sigma based calculations will be done. If you are doing normalization or simple regularization, there are plenty of techniques for this. So batch wise operations we are doing basically on multiple inputs that we are getting from the network. So altogether those batches will be processed. After this, pooling layer also we can add that we have discussed yesterday, and three types of pooling layers we discussed: average, max, and sum pooling layer. So I'll not go in depth with this again. All these things we have discussed yesterday, like stride size we can apply, or technique we can change while developing your model. So maybe for one data set, if max pooling is not good, we'll try with other pooling technique like sum pooling or average pooling, and then we'll try to see what outcome we are getting. Some researchers even try to design their own pooling technique. So they will just present new copyrights on their new pooling layer designs, and they update or they create advancements in the CNN. That also some of you can do depending upon what kind of processes you are trying to achieve. Then we have flattening layer. This, although we have added yesterday, but we have not discussed this in detail. So what this flattening layer does basically, it will help you to get metrics from all the pooling processes or the previous layers that we have, and then convert it into a single dimensional array. Based on this single dimensional array, the final decisions we are going to make. So this is basically organizing everything into one dimensional at the final stage of your CNN model. While making this your flattening layer, you will also have a few additional things, like we have some dense layers, we have your fully connected layer. This one, although we have discussed yesterday also, like fully connected layer we add on the last element. But the main idea is to get single dimension pattern to match it accurately with the labels of your data. So all the calculations that we are doing is basically to match with the label, how accurately a particular label we are going to match. That will be decided with this flattening layer by the end. So you can see here the fully connected layer also we are adding, for instance, and this I was giving you as an example. So when we are updating feature after feature, layer after layer, every calculation we are updating, so a set of neurons will be getting excited or inhibited. So the same is happening in the CNN. You can see like one color I have assigned for dog and other color I have assigned for the cat. So how many layers or how many connections at a time are going to be activated to make decision about certain specific characteristics in the future? That will help in prediction, final prediction, whether it will go with class 1 or whether class 0. So that will be based on the excitatory or inhibitory action of your layers inside. So these calculations that we are having level after level, how they are being contributing to the final calculation, how what sum we are getting from that, what pooling technique we are applying, that will contribute to the final number over here. This is the throughout process we are getting layer after layer. There is one more important part, that is your dense layer. This dense layer, as the name indicates, it basically forms huge number of connections between the two layers. Anywhere we can add in between this dense layer. Like if we have a dense layer to be connected between two layers of size n1 and n2, there will always be n1 into n2 connection. Why we are saying this? Like you can see here, if this is layer 1 and this is layer 2, you can see this x1 connected with the red wires, it is connected with each one of them. Similarly, x2 connected with the blue wire, it is again connected with each one of these. Means all neurons from the previous layer are being connected to all neurons in the next layer. So this network becomes a dense network, because in your CNN you are going to have like thousands of neurons on every layer. And when we are going to connect each one of them with each other, the row vector is also going to be very big, and there will be huge calculation that we are making. And how many dense layers we are adding into the network, that will also increase computational complexity of your network. So how much time your CNN is going to take, how good calculation it is going to make, or how complex your network will be, or main point, how well it is field deployable If it is a very complex or power hungry or maybe memory hungry network, due to this huge number of dense layers, that will also be a problem. So we have to be very careful how many dense layers are good enough for your model. Sometime for a very basic data set, maybe only one dense layer is enough. Even without dense layer, sometimes CNN will work fine. And sometimes for a very complex decision that we have to make on a very huge data set, maybe multiple dense layers you have to add. So for the dense layer also, again, how you are updating the inside rules or what hyperparameters you are updating on the dense layer, all those things are going to matter. So that we will discuss in the implementation also, that what parameters you can update throughout this. Then there is another important part, dropout layer. This dropout is basically a part of regularization technique. I'll discuss this also in detail further. So dropout helps you to prevent overfitting in the model. Overfitting we discussed yesterday also. There are some chances of overfitting and underfitting in your models. That is common with all types of model, whether it is machine learning, ANN, CNN, or any other deep learning model. Overfitting and underfitting are common issues. So if anyone is not aware with these terminologies, a simple layman language understanding we can develop is, overfitting is when your model is good enough with the training data set, but it fails on the testing data set. That is overfitting. It is overfitted on your training data set, but it fails on the testing data set. Underfitting is when your model is not even good for training data set and not it is performing on the testing data set. So that is underfitting condition. Both are harmful for a model deployment. If any of these occur, they will definitely destroy your model performance. So better to avoid both of these conditions. And there are several settings that you may have to do on the system, on your model, to avoid these conditions. Plenty of things are there that we can do, although we cannot discuss all of them here. But yes, one thing we can do is dropout layer. So dropout layer basically helps you to randomly switch between percentage of neurons in the network. So we recently discussed that when we create layer after layer combinations, the number of connections go very huge. But sometimes what we do is we add a dropout layer in between. That means instead of doing connection from one neuron to other, every other neuron, like we have done here, we try to drop out some connection randomly. Like maybe this connection will be dropped out, this connection will be dropped out, sometimes this connection will be dropped out, and we just try to see that what minimum number of connection can still give us best outcome. So that means dropout in between. So this will be generally applied after your dense layer. So once we have understood extracted pattern from your fully connected layers and the dense layer, then we try a dropout also. That if we reduce those huge number of connections somehow, how well we can get output on the lower layer. So you can see one example of this here. If this was your actual connection, we'll just try the dropout in between. Some connections we have disabled, and then we'll try to see if it is still performing better or not. Sometime we can switch off like 50% neurons, sometime we can switch off like 30% neurons, and we'll see how well our model is performing. If it is good enough, then okay, we have saved some computational power on your model, and it is good enough to work even on a smaller memory system. But if we have to use all the connections all together, then maybe you need a power hungry deployment system also further for these kind of models. The last part we have here is the softmax function that we have used yesterday. We generally prefer it on the final layer of CNN. And cross entropy, this one also we discussed yesterday. I use this as your one of the parameters inside the CNN model. So here what we are doing is softmax is again a kind of activation function that is preferred on the final edge of your CNN models. And in this softmax, basically what we are trying to do is, the idea is to update your outcomes based on this formula. So this is all about how your these z elements is the previous calculation values that we are getting from the filters. So we'll just update them into the formula, and we are trying to get function of z out of that will give you this final number. So whether your this outcome that we have calculated from the previous class, whether it will belong to class 1 or class 2, that decision will be finally made by the softmax function based on this calculation. So Z value will be updated in this equation, and then it will make decision which one is on the majority side, and that will be considered as your final class. So this is then finally your complete network that we get with different types. Although this is just a short network I have added over here. So based on the image training that we have done, your model will make decision whether the image belongs to horse, zebra, or dog, whatever we have. So this is just one example. We have one set of convolution layer, then we have pooling layer, again convolution, again pooling. So we can have so many layers of such type. And then we have several fully connected layer, and you will observe here one thing. We reduce it step by step. This will be a very huge number of filters and connections. We reduced it step by step to achieve the final level. So final level will include the number of neurons based on the number of classes you want to make. Like if I have to make 3 classes, on the final dense layer, I'll have 3 elements or 3 neurons setted into the filter. Before that, I'll add multiple layers that will help me to drop down this one by one. So accordingly, I'll set parameters of my model to achieve the final class. If there are 10 classes that I have to make by the end, so here on the final layer, I'll add 10 neurons accordingly. So final decision is always based on the final number of classes we want to make. But these decisions are always hit and trials. You cannot always say that I'll reduce it by a factor of 6, I'll reduce it by a factor of 4 and 2, then I'll get the final outcome. This will always be based on the repeated trials, on which setting your model gives best performance, that you have to achieve with the multiple training phases, multiple hyperparameter tuning. This is where the real time we have to apply while building a model. That is why we say that it is not like a 1-hour job. It requires multiple days, multiple efforts, multiple settings to achieve a final model. This is why we call it a part of research. Every day we have to try something new and then get the outcome out of this. Now, let us get a quick idea of overfitting and regularization with the detailed concepts over here. So this, the problem of overfitting, the general idea about this I have given to you. How it happens basically, when your data set is getting too much information from the training, even if there are noise and outliers, it is learning everything. Even noise it is considering, outliers it is considering, everything it is considering, and that is the main reason that it works. It seems like it is working good on the training data, but it ultimately fails on the testing or unseen data. So this is the main curve that we have for underfitting and overfitting. So here you can see, based on whether your model is underfit or overfit, your validation training error will change. So like here it is starting when we have underfitting. Sometime maybe your training error looks on the higher side over here, but as the underfitting goes, your training error will be reducing, and ultimately we'll see that your model is not good enough. Same goes with the overfitting also. Either your training is not learning enough parameters, or otherwise your model may be learning almost everything, even the garbage from your data, everything it is learning. So idle fit is the middle one, when we are just in the middle, not underfitting, not overfitting, just a good position between your validation error, training error, and testing error. That is the position we need to achieve from your model. So there are multiple regularization techniques. In order to deal with this issue, we apply different regularization techniques. And some of these we have discussed here. One is the dropout that I already added. Batch normalization is also going to help you with the regularization. If you find that your model is facing any of these problems, you just try to add some batch normalization layers in between. Pooling layers will also sometimes help you to reduce these problems. So if you have created just a basic network and the pooling layer is having very small dimension, just try to increase its dimension, or maybe you add multiple pooling layers, or just try to change your pooling technique. Maybe if you are using average pooling, try to change to max pooling, or maybe to some pooling, or any other pooling technique, and just see that if your model performance is changing or not. Similarly, you can try different levels of dropout also, whether you switch 20%, 25%, or how much percentage of neurons you are changing. So accordingly, some new features will be learned by the model, and you will get a better outcome from there. Similarly, sometimes we apply early stopping. This is also one important part. Sometimes what happens is, if we do not stop model training on right time, it will learn garbage features after that. So early stopping is also one part. So if you feel that your model is not improving its performance after this particular value, even after multiple iterations, so we add early stopping. Like maybe initially we have targeted that we will train our model with 200 iteration, but you feel that when it reaches 99 iteration, up to maybe 1/10 iteration, there is no change in accuracy and loss parameter. So you will see that your model is stagnant now. So instead of running 200 iterations, we'll just stop it before 110 only. That okay, fine, this is the final ability of my model for a good learning. After that, I can skip iterations. So that becomes a part of early stopping. This early stopping can also work as an hyperparameter in your CNN model building. You update its value, like I'll have a patience parameter of 10 for early stopping. Patience parameter of 10 means for how many iterations I'll wait before the value changes. So maybe if for the 10 iteration there is no change in accuracy parameter, I'll stop. So that patience parameter you can add as per your choice. Sometimes we add a small patience parameter, sometimes we add a large patience parameter. Accordingly, it will work. There is one creative process also, noise injection. This is about adding some noise to the inputs or the outputs of the hidden layer during the training process, so that it becomes more robust and it doesn't have a weak generalization. Why we do this? Now many of you may have a question in your mind, that what is the purpose of introducing noise into the model? This is not like a random noise. There is a specific type of noise that we can add. And why we do so? Just understand the scenario that you have trained your model on a very fine set of images. You have obtained a very huge resolution image and you have just trained your model. But your actual field requirement is to deploy this model. For instance, you have trained your model on a CCTV camera of very good resolution. And from there, it can identify people very precisely. But then when you deploy your model, or maybe you create a sellable product out of that, maybe it will be sometime it will be used with low quality CCTVs also. So in those cases, when it will get some low quality images, it will fail, or it will give lesser accuracy. So it will not be able to identify people out there. So what we do is we try to make our model robust. Even if you are getting good quality images, we introduce some noise in between, just to see if your model is able to detect that noise and it is able to still get right picture of the person. It is able to detect that person right or not. So this is how we make models good enough for the real settings. We just don't make models for the lab settings. It should be deployable in the real settings. So that we can do with the noise injection. Data augmentation, this is another important part. This we are also going to discuss in detail in a coming session also, maybe tomorrow. So this is about changing your data set, adding diversity in your data set by using some additional transformations, like maybe rotation we can add, scaling we can add, cropping we can add. We just try to change our image types so that we can have a diverse training process of the model, and ultimately we can get something out of that. The last one you can try is L1 and L2 normalization. I request you all to mute yourself. So we are having L1 and L2 normalization. That is also one possibility. This is basically to add penalty to the loss function in the system. Like for instance, yesterday also we have used some loss function, that was cross entropy I used over there. So this will help you to decide how well your system will deal with the variations or the fluctuations in the system. So penalty, like we do in case of recurrent networks also, if any of you have understood about recurrent network somewhere in early stages. There also a reward and penalty based training we do. If your model is not getting uh, can someone from the coordinators help me to mute this person, please? Ma'am, Abhilasha Sharma, can you please mute yourself? Abhilasha ma'am, can you please mute yourself? Thank you very much. So this is for the L1 and L2 normalization. We add some penalty into the system to make sure that whenever any weight change occurs or whenever we are updating any feature selection, if the model goes in the wrong direction, it will get some penalty. And with that penalty only, it will understand that, okay, I'm going in the wrong direction and I have to prevent this and I have to choose some other way out to extract. So sometimes we prefer penalty-based learning. If the model is not extracting relevant information, we will add penalty. And how we are going to make decision about that penalty? Very simple, because we already have labels. So if your model is in the training phase is not good enough to match with the target label, we'll add a penalty to that. And we'll try to derivate our model or deviate our model from the current performance, take some other path to get the feature maps, and then ultimately we'll try to achieve to the final level. So this is the entire process we'll have with the CNN when we try to improve our model, when we try to enhance its outcomes. So these are the all things we do. The layer after layer additions I have discussed, the essential layers we have discussed yesterday, the additional layers we have discussed today. So this forms all parts of your theoretical system. But how we do this inside your uh, development phase? On the Python, for instance, we'll be doing that. So I'll be again using this Google Colab platform, and if you have seen in your timetable also, we'll be using CIFAR-10 dataset today. So the same I'll be updating right here. The snipper window I'll open up for you, all of you side by side, and I'll be keeping all the dataset right there so that you can access it side by side easily. So here on the same, I'll be sharing the link also for this, don't worry about that. So I'm updating here day 3 session 1. So I have just created one. This basically I'll be using day 3 session 1, and I'm sharing the snipper link also with all of you. So here I have updated, and this sheet I have opened up here, and all of you are just requested to do it parallelly so that we can understand the process. Although several things we have learned yesterday only, so we'll follow the same technique over here, but if there is any new thing, that I'll explain definitely in detail. So the very first task that we have to do, if anyone can let me know in the chat box, what we do generally at the first step. We have done this so many times now, so I think most of you, yes, loading libraries, the necessary libraries I'll get, load necessary libraries. Thanks for the quick response in the chat box. So there will be again several libraries that we need. One we need is TensorFlow, the main library. TensorFlow framework we'll be using for the deployment. Then we definitely need some basic libraries also. That is your NumPy will need, and Matplotlib also will need for some plotting task. Matplotlib.pyplot as PLT I'll call. And then different layers from my TensorFlow for building my convolution network. Yesterday we have called few layers. Yesterday I have used one basic model only. Today I'll use one different approach to build a convolution 2D network. See, there are like hundreds of different ways to design CNN network. I'm just following one way out. You will, when you start working on real-time practicals, you will find several ways to do this coding. This is just one sample we are discussing here. It is not like this is the only standard method to do, because you can take help from Keras layer sometimes. Sometimes we build it directly with the TensorFlow framework. Sometimes we take help from the sequential model. Sometimes we add layers directly without sequential model. We use input layer directly. So there are different possibilities. Each one of the patterns, it just depends on what type of libraries on the backend you are using, what framework you prefer, what interface you prefer. Such as sometimes people like to work on TensorFlow framework and use Keras interface with that to get an easy access to all the layers. Sometimes people don't like to work on Keras interface, rather they just stuck on the TensorFlow and they try to extract layers from there only. So all the options are there. Currently, I'll be updating here one simple technique, the basic libraries I have updated. Then from TensorFlow dot keras dot layers, I'll be importing. Yesterday I have imported sequential model. Today I'll not be taking help from sequential model. I'll just show you one more pattern. I'll use directly the convolution layer, then convolution 2D I'll use, then dense layer I'll add here, flatten layer also I'll add here, and dropout also I'll add. Even we can have max pooling layer, so that also I'll add over here, max pooling 2D. These are the essential layers. If we need any other layer later on, that I'll add as per the requirement. We can do that whenever we need in between. Again, I'll get, for instance, one models. Instead of getting sequentials model, this time I'll use just one empty model on which I can build my input layer directly. There are different types of models that we can call from the Keras interface directly. So from here, I'm just going to the model section, and from there I have a keyword model to call directly, in which I can put all the layers together. Yesterday we started with a sequential block. Today we are following a model based approach where we'll merge all the technique. So this is the first step I have done. I'll just run this path, and if it works fine, I'll share it with all of you. For the first run, it always takes some time, especially when you have TensorFlow in process, because TensorFlow is one heavy framework that you are going to use here. So accordingly, it will take some time, and I'm sharing this in the snipper window in the meanwhile. So on the session 3 window, basically, I'm updating it. And here on the chat window is this functional approach regarding what? Please let me know what you are asking about. So after this, I'll be updating. The second task we have is load dataset. Once your libraries are ready, we'll get a dataset. So again, we are not going to get any dataset from the folders here because we have lesser time, and uploading folder dataset takes like so much time for in case of images. So better to get dataset from the online sources directly. They are easy to access. Uploading dataset from your model will again take so much time. So we don't have that much time in the session itself. So what I'll do here is load the data, then that will be my CIFAR-10 dataset. This is basically a containing classification kind of images with 10 different classes that include some animal images, some vehicle images like airplane, etc. There are plenty of labels. We'll discuss that further. So what I'll do here is CIFAR-10 variable I'll choose, and then tf.keras.datasets, I'll go to this module, and from here I'll just get CIFAR-10. You will have CIFAR-100 also. That means 100 classes. We are using mini dataset with 10 classes only. The second thing we'll do is distribute this data into train and test set. Initially only, I'm just separating everything. So we know how to do this. I hope yesterday also we might have done this. We have a direct approach over here. There are two things. One is using train test split. That also you can do. If you have everything in a single folder and you want to split it manually, you can take help from train test split function. But for majority of the online datasets, when we load it, it automatically gets into train and test dataset because this is how they have organized it on the servers. So what I'll do here is, instead of using my train test function, I'll load data directly from the CIFAR-10, and it is already in the form of train and test, and it will get it automatically from there. In case if you are working on your self-designed folder where you have everything on the single platform, in that case, you can use a different technique. You may have to use train test function in that case. I'm using the standard approach based on the server-based libraries. So I'm using xtest and ytest. two sections my load technique will give me. So that I have updated here. Load underscore data, I'll be updating. So cipher R I'm missing here. So CIFAR-10 load data function I'm applying on this, and this load data function replies in this format. First it will give me X train, then it will give me Y train, then X test, and then Y test. So the same pattern I have to follow, because this is the return pattern of the function. If you have studied about Python functions, there is a return pattern of every function, that what parameter it will return first, what it return second. So accordingly we are getting it here. Then print. So for all of these we can check definitely the shape information. Yesterday also we have done that. So let me update the shape information, and then I'll share the code with all of you. So this quick information will try to print here. And this is again a very simple data set with around 50,000 images in the test, in your train set, and around 10,000 images in the test set. So you can see right here. And this shows that you have RGB images. 3 you can see here. This is basically by default a RGB sequence. And this is your size of the images. This is the count of images that you have in every section. Here we have single element for labels. Means directly the label is highlighted over there. Maybe they have organized it in a specific pattern. I'll show that also to you, that how it may work. I'll just update this in your Sniper window. I'm updating it here also. So let me know when you all are ready with this data set. I'll wait for the responses in the chat box. Thank you very much for the updates in the chat box, everyone. So we are moving forward with the next part. I'm sorry for the background noise that we are getting right now, because some election related activities are going around, so I cannot control this. Just for a few minutes it may happen on the background. In the meanwhile, I'm just updating here a small set of code. For instance, we just want to see, same as yesterday, we just want to see what image we contain here. So this you can see one image we are getting, or we can try others also. Some type of, like, this is a truck, I think, a truck type image, or maybe any other, like two, I'll check. So this another, I think, aeroplane or something, it may be. We have a small size image, so something from the vehicles or some kind of animals. This is a mixture type of data set. Then we have size of the matrix, then we have the RGB sequence. And if you want to see this data set, you can see right here. So this is your sequence, and you will observe here that now we have bigger values. Why? Yesterday what we have observed is there were zeros on the corners, but today what we are seeing here is we have everything lined up with higher values. Reason being, today we have one thing is that there is information on entire image. There will be some pixel values on the entire image. Yesterday what we were having, just a number in the middle, and the side patterns were black only, because on the black pattern there was a number printed with white. So definitely on the edges there we were having zero information, and in the middle only we were extracting some elements. But when we have this type of data set, like animal images or maybe some nature images, there will be pixel values throughout the image, because certain color variations will be everywhere. So all the pixel elements you will see based on that. So 0 to 255 on 3 scales RGB on 3 channels will be updated like this. So this, although we cannot see all channels right here because there is limited capacity of Google Colab to show you the metrics, but still this is a way we are getting. We'll see numbers everywhere right now. So what I'll do here is, while getting this done, for instance, if we, okay, initial we have already seen. If I want to see maybe Y train, let us see what we have. So it says array with 9 values over here. So this is how they might have arranged it in the form of arrays. So this pattern they have as a by default pattern they have. Will update it further as per our requirements. But the initial things we have seen from here. Now the next part I'll update here is little bit pre-processing for this data set, pre-processed data set, and we know how to do that. Yesterday also we have done. Yesterday what we did is we did I think two things. One was to reshape your image, and second was to normalize your image by dividing by 255. Two things we have done yesterday. Today I'll do one different technique. One okay, that will be normalization only. Second, I'll use flatten for my labels. Flatten means recently I got here matrix like 9 elements of array to represent my label. I'll bring this to single value. Let us see how we'll do that. For instance, the first case I'll use is reduce pixel values. So let me first print it here for so that we can compare also before processing. For the second only, I'll put it here. So I'll just, this is my original data. Let us see what we get after reducing pixels. So now again, I'll create here xtrain and xtest. This reduction or this normalization we always apply on X dataset only, means on the features only. So the same we are doing here and divide by maybe 255.0. And similarly, I'll do it for the test. This time I'm not using the the minus factor. I told you yesterday also we can have different techniques. Yesterday we used 1 minus 5 factor also, minus 0.5 factor also. Today I'm not using that. I'm using different normalization, just dividing by 255. Because today already we have on the higher scale values. Yesterday most of the values were 0. Majority of values were 0. So if I divide it directly with 255, we will have sparse data set. Sparsity is also one problem in processing your details. So instead of having sparse data set, I used minus 0.5 so that I could remove those zeros to a specific number. That was minus 5. So those things we make decision based on the pattern of your input data set. Currently, I already have high value image values on the entire image because there is some color distribution throughout the image. So I can just divide by 255 without requiring any subtraction factor over here. Second thing, we have one technique I'll use is flatten the label. And you will see here what we'll do for this very simple technique. This is basically a kind of normalization I'm applying on the labels only. So instead of having a matrix of 9 elements that I have seen earlier, an array of 9 elements, I'll try to get it into a smaller scale that will be with the single element. Let us see what we'll get. I'll first run this, I'll test it, and then I'll share the code with all of you. Now, first, let us see the xtrain for the same set. This 2, I'll just use it on the same element right here to compare outcome. See, now we are on the smaller scale. So the division we have done based on the 255, and now we have reduced it from 0 to 1. The same thing I discussed in the theory also. The same we have done here. Second is on the Y data set. So for this also, let us see what change we are doing here. So Y train, and again on the second element. So getting class value 9 only. This is not array now. Not array 9, rather value 9. For example, I'll do it for the 1. Then it is single array again. Single element. So only not array, but presented into the single element. So this is one difference also we'll have in comparison to yesterday. Like yesterday, what we were doing is your sequence was in the form of 2 categorical. One thing we added in your label classes, whenever we deployed labels, we used one function 2 categorical. Today we'll not need that because I have already flattened my these outcomes. I have already brought it into a single element value. So that will create a difference. Like you will see, if I check my 5th, the target value is 1 for this. If I check my 10th, for example, 10th image, the target value with single element I have given means classes are updated. This is 4th. So it will just scan through all the classes. Like for train, maybe it is giving class 1. For horse, it is giving class 2. For airplane, it is maybe giving class 3. So accordingly, that value I'm getting from here. Earlier, if I check why train 10, okay, I'll not be able to get it now because I have changed on the same values. Later on, you can try by using different values. So earlier it was an array, but now we have single element value for the class representation. So I hope this is clear for everyone. And now I'll share this code also with all of you. You can conduct the same test. Let me know when you all are done up to this, and if the concept that I just discussed, this is clear to all of you. I just compared the changed data set after pre-processing. I'll wait for the responses in the chat box. Thank you for those who are responding. Okay, great. So I just believe that a majority of you might be done. If I need to wait for anybody, just let me know in the chat box. Otherwise, I'm just proceeding ahead with the plotting task. Let us just visualize some of the images from our data set. Like I'll try to plot a few set of images, maybe 10, 20 images we can plot instantly to see what is contained inside this data set. Although I'm not going to plot a very big size of images, just small size images will plot. It will not be like a high resolution image because we are plotting it on the smaller dimension, but still we can at least see what is contained inside your data. So let me write here, visualize data set with a few images over here. So first I'll set my figure and axis information. I'll be creating subplots because I'll be plotting multiple images over here. So maybe 5 cross 5 is my figure size right now. K, I'm using 0 for the iteration. So for I in range, I'll use, for example, 5. For J in range 5. If anybody need to understand what we are doing here, is there is a simple thing. I have created subplots 5 cross 5. So how I'm going to distribute my subplots? For that, first I'm doing iteration row wise, then column wise, and the same I'll be updating ij in the axis. So axis I and axis information ij. So based on this, like first iteration on 1 1. So accordingly, on the first subplot, the image will be plotted. Then 1 2. So on 1 2 position, the image will be plotted. That we are doing here right now. A simple coding sequence. I am sure inside this, I'll pass my parameter for x train with k starting from 0th index. I have given it k equal to 0. So it will start from 0th index. If you need any middle value images, you can update index accordingly. Aspect ratio, I'll decide is auto. So based on the subplot size, the aspect ratio of the figures will be updated by the system automatically. And after this, every time I'll just update my k. K is your index. So I'll start with 0th index value and then update every time when the loop runs. So a simple sequence of coding we are doing here to visualize first few images. It will take some time since there are multiple images to plot. So you can see some animals, some vehicles, some birds. There is a mixture of data set inside this CIFAR-10 data set. All of you can try and plot this. see how it works. So I have added this one right here. Okay, I may have not added some section in this part. So let me just update from here onwards. So this is what we are getting as an outcome. Let me know when you all get this and you got the idea of this code also. A very simple Python code we have updated here. You can try different plot size also. Maybe if you want higher number of images, that also you can try. So as I told you, when we are building a machine learning model, not much pre-processing is required. We can feed raw data into the model directly. So instead of using so many pre-processing ways, we'll just use simple pre-processing with the normalization in the beginning, flattening for the targets, and I'll just build a CNN model. But instead of using a simple CNN model, this time I'll add so many layers into the CNN model. So here I'll be writing a lengthy code in the next section, but don't worry, I'll explain everything to all of you. First, try to listen what I'm explaining while writing the code. The code I'll share after that. So don't worry about rushing to write everything. Just understand what we are doing. First of all, I'm just updating here number of classes. I'm updating it with the k parameter. The length I'll get from one function that we have. A by default function is available in Python. Y train will use with the set function. It will directly calculate number of classes in your y variable or the target variable. So this combination length means throughout the length of Y-train dataset, it will just prepare sets of your classes, individual classes. So we can print set from here, whatever k value it gets, although it will get 10 only, we know that. But still, if you have some unknown dataset in future, you don't know about classes of it, we can use this technique in that case. Next, I'll just update build model using functional API. This is the technique I'm following. Functional API technique I'll be following with the model technique, that because model I have used in the beginning. So I'll just insert the first element, that will be my input layer. And for instance, input layer I'm initializing inside I variable. So input, and inside this first parameter I'll pass is a shape parameter. And shape I'll decide based on what I get on the first index values. And this is the easiest way to get shape. I think all of you can understand it easily. Shape function we have used several times with the dataset, and we have seen it here also in the beginning. This is the easiest way to get shape of your data. So the same I'm passing as a part of my input layer, so that my model can understand what size of this image I'll get. So it will get this one basically, because I'm using it on 0th index. If I use it on the entire dataset without index value, then it will get this entire. But on the input layer, we just need to mention this, the dimension of your per image. So that we are updating by using that index 0 element. First thing. After this, I'll add my other layers. So I'm updating other layers into X. Input I'm declaring separately. Then all the convolution layers I'll add into X. And ultimately, I'll combine this I with X by using that model function, and your model will be ready over there. So convolution 2D is the first important layer I'll add. For instance, I'll start with 32 filters. You can start with 8, 16, or any number of filters. We generally take these even number filters out there, most preferably. But although in literature, you will find several recommendations for this. So depending upon what domain you are following, just try to follow literature from that domain. accordingly you can get the updates for the technique over there. Activation function we already discussed. In the intermediate layers and in the beginning layers we prefer ReLU, and in the final layer we generally prefer Sigmoid. So the same we are using here. I'm adding a padding option also here. And finally, we are connecting this with the previous layer, that is my I layer. So here I have updated, because layer after layer we have to build connection. And this, in the functional API technique, this is the way to connect with the previous layer. In the last of your sequence, we'll update the previous layer number if we are giving a specific variable to that, store that layer. So this I have updated so that this first layer gets connected to this previous layer when I'll build my model finally. I have used one more element here. Padding is same. This means when we'll just use your input, a certain specific size of input on the your layer, same pads the input so that output has the shape as that of input only. So same means the shape of input will be carried forward to the output also. And in this case, the stride size of 1 only will be supported by default. That is only how we'll get same shape if the stride size is 1. If we have more stride size, your dimension will be reduced accordingly. So by default, same padding is going to get your stride size of 1, and accordingly a same output, same size output it will convey to us. After this we have a batch normalization layer. This, all these layers we have discussed by now. So batch normalization layer right now I'm adding without any default parameter. uh, Means without adding any hyperparameter. I'm using empty bracket, means only default parameter I'm using. Let me see if I have loaded batch normalization layer earlier. uh, it looks that I have not loaded batch normalization layer. Yes, I missed it. So I'll just update it here. That is why I was getting that red line below my code below. So batch normalization, I have updated right here, and I'll just run this. Okay, my layers are freshened up now. So let us go down and the error should be gone. Yes, now I do not see that underline, that red underline, because the layer is ready now. So batch normalization I have added with the default set of parameters, and this will be connected with the X now. The previous I have stored in the X only. So now I'm updating everything in the X only, but layer by layer connection will be updated with the help of this bracket variable that we are adding by the end of the layer information. The next layer, for instance, I'll be adding is maybe again a convolution layer. For instance, I'll pick up this right here. Now I told you that we can have any big model. You can even have like 10, 100 or any number of convolution layer. I'm just creating multiple layer, multiple random layers I'll be adding. When you will do it with your data set, you can follow a specific pattern out there. I can see some hands raised also. If you have anything to discuss, please let me know. You can put in the chat box also. I'm just reading your comments side by side. If there is something urgent that we want to discuss and you have raised hand, just let me know quickly. Or maybe if you have a possibility to unmute yourself, that also you can do. So I'm updating one more convolution layer over here with the same information, but I'll be connecting it with the X layer now, because layer after layer I'm making connections. So previous one is your X. So same I'm updating here. You can change filters information over here. The number of filters you can change, but in my case, I'm using 32 only, for example. Again, I'm adding one batch normalization layer with default values, for instance. You can do again different hit and trials you can do to check which one modeling works well with your data. I'm using just one technique here. Mixed pooling 2D I'm adding with a filter size of 2 cross 2, and I'm attaching this again to the previous layer right here. After this, for instance, okay, I'll just separate the convolution sequences with the gap. Again, I'll update this convolution layer in my network. This is how in-depth feature maps we are trying to extract. that possibility we are discussing right now. So someone is asking about what we have default parameters for these layers. Don't worry, let me just finish this. I'll give you official sources for this, because it is not possible to discuss all the hyperparameters over here. I'll show you some official sources from where you can take reference as a beginner to understand default parameters of layers. So that is basically possible from the Keras or TensorFlow platforms. So we will do that later on. First, let us build this model. So max pooling I have added, and on the next, again I added a convolution layer, but now with the increased filter size. What we do generally, prefer technique is start with lower number of filter and then increase gradually. So start with maybe 8, 16, 32, and then keep on increasing further layer after layer. So 2 times I have used same size filter, then on the third stage I have used 64. Sometimes you will use on the second stage only 64, then maybe you will switch to 128, then maybe to 256. This is how in-depth network you want to create. Accordingly, you can keep on updating. Remaining things I'll keep as it is. I'll not make changes to this. And for instance, after this, again, I'll add batch normalization, just depth I'm adding to my network. And after this, again, I'll add one more convolution layer. You can do anything with this because currently I'm not following any literature sequence. I'm not just considering the specific data set. We are just learning, adding depth into the network. That only one thing we are learning over here. So this sequence I have updated. So after this, I'll just get into the sequence. We will update maybe a max pooling layer also after this. So this I'll also add. The filter size you can change, or you can have different options on different layers. That also we can try. After this, I'll just copy this entire sequence and update it right here with a different filter size, like maybe 128, 128. So this I have updated here instantly, and depends on how many layers you want to add after this. For instance, I'll stop here, and now I'll add my closing layers after this, a step-by-step sequence for that. First, I'll add my flatten layer, again with the default parameters, for instance. And then I'll add, for instance, a dropout layer. A dropout I'll drop 20%. So 0.2 I'm using. You can use 50%, you can use 30%, any hit and trial you can do. I'll drop, or means switch off maybe 20% neurons while using this dropout layer. After this, for instance, I'll again go to the final phase, that is your dense layer. I'll add with 1024 parameters, then we'll add activation equal to ReLU over here, and then add X. Then we'll add dropout 0.2 again, and X. Again, any number of dropouts you can create based on your requirement. I'm adding 2 levels of dropout over here. Then again, I'll get my this dense layer. Now, for instance, the final stage of dense layer I'll add. So I'll copy this part and I'll update it here. But now with K. Why K? Because this we have calculated right here. The final number of neurons on the dense layer will be based on how many classes you want to predict. And now the activation will also change on the final layer. So it will be softmax now, because this is my final layer. So let us see model information with connecting input layer and convolution layers, along with all the additional layers of convolution neural network that I have updated into X. So I'm just building my model right here. Finally, model description I'll be getting. So model dot summary I'll be updating here. So this is an initial set of variable I have updated. When I run this, a model summary will be printed. But if my model is not suitable for my data set, that I'll not come to know here. Why? Because I have not applied my data on this. I have just created an empty model right now. When we will deploy this model on my data set, then only I'll come to know whether this is compatible with my data or not. And in that case, we may need to make some changes into this. But currently, you all can build this dummy model and we'll deploy this on the dataset, and we'll see if this is possible to use on our existing data set or not. So let us see that. I'm not sure if I can post this entire big calculation on the chat or not. I'll just put it in the parts for those who are doing it from the chat. So all of you just build this model, try to understand whatever we have updated inside this network, the structure you can see here, the inside parameters, these values are updated automatically based on the hyperparameters that we have added into the models. So we cannot control them directly, but yes, indirectly we can control by changing hyperparameters. So this is the final trainable parameters or non-trainable parameters that we have inside the model. Some are the fixed parameters based on the what layers we have added. So all those informations we have right here. Let me know when you all are ready with this. I'll wait for the responses in the chat box. I'll wait for the responses for a while. When you understand this model building process and you build it, I can see a few responses over here. That's fine. So we'll just compile our model now. I'll add one more part over here and let us see what we get. So compile will do model.compile, and inside this optimizer I'll use same as yesterday. Don't worry about this, because in future classes we are going to discuss this in detail also, that what are the possible optimizers that you can use. Loss function I'll change today. Reason being, yesterday I was having your categorical sequence, that was an array sequence for my target variable. Today I have a sequence with single variable because I have already flattened my target variable. So I'll use sparse cross entropy in this case. The loss function we keep on changing depending upon what type of target parameter we have. So this one is more suitable when you have already flattened our target variable. Matrices I'm adding here is accuracy, since I have this as a classification model. So let us see. We'll just compile this model. Okay, this is working fine. So all of you can compile it, and then we'll pass data to this model. So the next part here is to train my model. In order to train this model, the process is very simple. We'll have learned it yesterday also. We'll use fit function directly. So for instance, I'm storing my model into R parameter over here, and I'll use model.fit with this. Today, I'm not using validation dataset. You might have observed that. Yesterday, I have used that. So this is your choice. If you want to use validation dataset separately, you can create a validation set. Today, I'm using only test dataset as a validation dataset directly here, because I'm not going to do a separate testing. Just to save time, we are using this. Otherwise, you can do all the separate tests also. Everything is possible. See, we are just learning the possibilities here. Otherwise, you can do any setting for your models. Batch size, for example, I'll update one random value of 128. You can change batch size. Batch size means how many inputs you want to process in one go. So I'll use like a 128 batch. Verbose I'll make equal to 1 or 2, any value you can give. If it is 0, you will not be able to see the training process outcomes iteration wise if it is 0. If we give it a number like 1 or 2, we'll see iteration output after every epoch. So that I have updated right here. I'll just run this, and 10 epochs just I have run so that it doesn't take much time. Later on, you can try it with like 50, 100, any number of epochs, and you can see what accuracy you get from your model. So this will definitely take a little bit of time to run 10 epochs, and then we'll be able to see the results for this. In the meanwhile, I'll just keep on updating some codes after this, because we have to plot accuracy today. And after that, we'll be testing label mapping also. So two things we have to do. So while it runs, I'll keep on updating next codes in the cells further so that we can run them immediately as the code finishes here. So you all can run it side by side. I'll provide this code so that you also keep on running this code while we learn the next code. So I'm just updating it here. And after this, I'll add here plot accuracy. So for that, I'll be updating my next error, plt.plot. Then we have history. From this model, basically, I'm getting my history, and that will be in terms of my measure parameter that I have updated during model compilation process, accuracy, that I'll just consider my prime parameter over here. Label for this I'll assign is ACC. You can give any name to the label on the, basically on the graph. That will do. Color to accuracy, I'll give red, for example. You can give any name. The second is validation accuracy. I'll plot validation accuracy. Why? Right now I'm using my testing dataset only for validating my model. So validation accuracy, I'll call it. Then here I'll write well accuracy, and label for this again I'll give well accuracy. And let us see, plt.legend. I'll update based on this. So I think this should work fine. Let me just verify. PLT plot we have updated, our history with first parameter, its labels we have set. Color I'll change, for example, for second I'll use green so that we can compare it easily. So these are different parameters. I'll not share this code right now because you cannot definitely run it until and unless this code is done. So the accuracy, I have created a plot sequence for this. I hope the code is clear. This is very simple code. We are just creating two plots on the same graph. So plt.plot, both time I'm doing here. And for those both line charts, we'll be just updating label accuracy and validation accuracy with different color information. After this, I'll do one more task, test label mapping. Yesterday, we have not done test label mapping, or this is currently, this is basically validation label mapping, because test dataset only I'm using for the validation over here. Just the name I'm giving it, although it will be using same dataset, the test dataset. Otherwise, what you can do is, in the previous stage, here you can pass your validation dataset, specifically the validation dataset, and here you can use test label mapping by using separate prediction sequence that we used yesterday also. See, I'm just telling you different options. How you want to deploy your final model, that is based on your learning. Whatever you extract from different things, different experiments that we are doing, you can build your model based on that. So first is label mapping. I'll be using here, because this time instead of getting 0, 1, 2, 3 labels, I'll try to get it with the specific names. So based on what we have in the dataset, I'm updating here a label sequence. This reference you generally get from the main source of data. So whatever we have inside this data, that I'm updating here. Dear dog, in the same sequence as they might be segmented by the system. So this reference you generally get from the source of your data. So we have horse ship, we have truck. These are the labels, and I'll just split them up by using split function. So currently I have chosen this as a single sequence and I did a split function, so they will become individual labels once I update it. So they should be 10 in numbers. Let me verify. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm updating 10 or 8 only right now. Maybe I have missed some labels in between, and this should be separate and this should be separate. Now this looks right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This should be fine now. 10 labels will get from here. Next, I'll add here, select the image from our test data set just to see the outcome. Image number, for instance, I'll start from 0. Then display this particular image, plt.imshow I'll use, and I'll pass my xtest over here with that specific image number that I have declared recently. Then next thing I'll do is load the image in an array so that we can pass it further. So I'll just convert this image into validation accuracy 80.06 you are getting. In my case, maybe if it is slow enough, then I may not be getting output. Let me rerun it. If you are able to get the output, let me just rerun it if it is slow. Those who are able to get the outcome, they can definitely share it on the chat box, what accuracy you are getting. That will be good. Maybe on my side, if internet is slow, or maybe if Google server is not connected well, then it may be taking longer time. But yes, if it is running on someone's system fine, you can just update everyone that what accuracy you are getting. The code I'll share, so next code also you'll be able to update based on that. So I'll put here your plotting code also, so that if it works on your system, you can plot the graph as well. So load the image in an array after this. For instance, I'll pass everything into a NumPy array right here, x.test image underscore number. There are so many ways to do test label mapping. Again, this is just a technique. That's just one technique I'm using. Later on, you can find several other options for this. I'm using reshape over it, that n with reshape, because I have one image only right now. So one in the beginning, and then shape of my image with 3 channels, since I have RGB image right here. So that I have updated. After this, I'll just make my prediction. Predict. So for this, I'll use prediction label over here. Then I'll use label sequence. Inside this, I'll pass my model and I'll pass predict function. Inside this, I'll pass my recently reshaped matrix with value P. And then I'll use argmax, one additional function I'm adding here. Why we need this? This basically helps you to return the maximum value of the target function that we are achieving from the probability sequence that it is getting. What is the maximum probability of a certain class that it will return to us? So that I'm adding into the sequence of labeling. Let us see what is the original label so that we can print it on your final figure. So that will get from the test data set directly. Y test I have updated here, then image number I have updated. So I'll write here one more marker, load the original labels. Then finally we'll try to display the results. So we'll just print here a sequence like original label is one simple technique I'm using. I'll update this with the format sequence. And
Madam, I think in the prediction label, there should be square brackets.
sir, I'll let you know what we are doing. Don't worry.
Thank you. Sorry.
This one, right. You are very right. So this one I'll change. Thank you very much. So here we are updating curly brackets because we have this for your formatting sequence. So I'll just update here the format. And inside this format, I'll be updating here original underscore label, predicted underscore label. So this will be formatted automatically. Original label will go to this bracket, predicted label will go to this bracket. Okay, there is some, okay, I am giving it a name, prediction label. So it's the same I have to use here also. The same name I need to use, prediction label. This looks fine. So this should be all right now. I don't need anything else, I think. So my model is still running. I cannot produce results after this. If anyone else is able to do this, you can just let me know. I'll just close this right here. I'll show you quick results with already run model on my system. So because we are on the verge of session already, and 10 minutes we have to spare for the discussions as well. So this I'll share with all of you. And in the meanwhile, just to save time, I'll show you what we are going to get from these sequence of codes, because my model is a little slow here. So I have a sample right here. I'll show you what we'll do. After building your model, when we train it, so this will be the epoch sequence. I have run it already with 20 different epochs right here. You can see by 20. So these values of accuracy, we are updating in sequence over here. And ultimately, I could plot my validation accuracies like this. The same code that I have shared, it will result something like this. If your that training process is fast enough, we can get this immediately, but we are stuck right now. So validation accuracy and your training accuracy, we are able to plot like this. Ultimately, the label mapping that we are doing, that we are updating here. So for instance, I'm testing it with the first label. So that is, first label is cat and the predicted label is also cat. So this image must be of the cat, because we are not printing here high resolution images. So but whatever we are getting is that it has mapped. So will compare it from here directly. If the predicted and original is equal, then means it is working fine. You can just simply change your image number from here to test it with the other test images also. Like there may be some images of airplane, truck or horse or anything else. Accordingly, you can see it in the outcome, and that should be equal enough if your model is good. So that we have over here.